Hi everybody, welcome back to Chem 161, or 160 something, 163 today. I knew that, I just don't know how to numbers. Happy to answer questions in the chat, please keep putting those there. While you do that, I'm going to post a problem on the board here. This is basically a review of what we did yesterday. So yesterday we actually did this problem. Let me go back. So we did this, where I actually solved for x using all the algebra, and then I showed you the shortcut method using a square root, because I had both initial concentrations were equal. And then I showed you Wolfram alpha. What I'm going to do is I'm going to put this problem on the board, and you'll notice that there's only one thing that's present in here, and that is the NO2. I want you to use any methodology you would like to tell me the amount of these things, i.e. their concentration, at equilibrium. So go ahead and start doing that. You're going to need to make an ice table like we did last week, because we want to be getting in the practice of making ice tables. Ice, ice, baby is going to be the theme for this class. Hopefully me just saying that doesn't get a copyright strike. We'll see. We'll see if Vanilla Ice hates chemistry. So go ahead and do that, and while you are doing that, I'm going to comment a little bit about what's coming up. So pre-lab number 1 is due by Friday at 9 a.m. Hard deadline on pre-lab, so I don't actually give you time after that because it's intended to be a pre-lab. So you have to do it before lab starts. Guess what also happens at 9 a.m.? That's right, you get to meet me in person. You're the first students in 2 years that get to do this. I don't know whether that is lucky or unlucky. I will leave that as an exercise to the student. But on Friday at 9 a.m., we're going to do our first experiment. So experiment number 1. You need to be present in Whitehorse 345 at 9 a.m. Please try very hard not to be late. I realize that 9 a.m. is prime traffic time. Leave a little bit early. I'm definitely going to leave a little bit early because I have to print stuff off before class. So my plan is to get there at like 8:15, 8:30. Yeah, we'll get started at 9. If you are late, you're going to be partnered up with whoever else is also late, or you might not have a partner at all, and I'll have to have you join a group, and then we'll figure it out for the next week. And that's awkward and embarrassing, and nobody wants that, right? The worst thing that could happen is you don't have enough time to finish the experiment, because you do have another activity to do before you do that, so don't show up 30 minutes late. Do you need to find a lab partner beforehand? No, you can find a partner on the spot. I know that friends tend to enroll in classes together. I certainly did that as a college student. And my intent is that you are working with either somebody that you have already chosen or somebody of your choosing. I don't choose lab partners. I let you guys do that because I'm not invested in it. As long as everybody has at least one partner in the class, I am happy. Can I explain question 6 in the pre-lab? I would prefer to do that on Discord. In fact, I think I already did. Let me read to you what I wrote there. So, question 6 requires you to read ahead and look at the procedure. Sometimes pre-lab questions will do that. Let me find the specific question. Because y'all are working on this problem, I assume. Did that pop up on the screen? It did not. Okay, so let me put 6 on the screen here. And I can just very briefly talk about it. Oops, that's not going to work. There we go. That's what I want. So there's question 6 from the pre-lab on the screen. So what I want you to do is, and in fact you can do this now because we're doing this calculation today, choose some numbers for concentrations based on what the lab is doing. So there's a very specific part in the lab that gives you the answer to this, and I'll actually point it out here. So in part B, where is it? Let me find it. You know, it might not actually be in the post. Okay, so here is the step where you're making the standard. And I want you to look at the concentrations of the things that you're using. So this is the iron 3 solution, and this is the KSCN solution. So you're going to notice that this one's way bigger than this one, right? And so back up here in the procedure, or in the descriptions, here's the answer that you're looking for. It's in this paragraph right here. So if you add a very large concentration of one thing to a very small initial concentration of the other thing, what happens? So play with the numbers. Calculate, and you can just pick any K you want to. Pick like 500 for your K, or a number. It should be a number larger than 1. So pick 100 or 500 or something like that just to simulate it. And then see what happens when you do this, and look at what the concentrations are. And so that's my hint to you. That's what I'm looking for you to do for problem 6. All right, I'm going to give you about, 5 more minutes or so to do this problem, because this is a pretty simple ice table. Go ahead and try this, and we'll go over the answer in just a bit. All right, let's do one more minute. We'll see how far we can get, and then I'll start the problem. All right, so I've already sort of set up the problem here. So there's our reaction, there's our K. So at this point, you definitely should know how to write the K expression at least. So I got products over the reactants, so there's my 2, so that's going to be a squared. I got N2O4 that shows up on the bottom. We're all set here to start this problem. So I'm going to fill in the numbers, and you're going to notice that I gave you a product and not a reactant, right? So this is what I have. Does it matter which direction I solve this? No, it doesn't. It's an equality, right? However, if I let this reaction go to equilibrium, I'm certainly not going to lose stuff from over here, right? I don't have anything to lose, so I can only gain stuff. So I'm going to lose some amount of NO2. And I'm going to gain some amount of N2O4. Now, how are those related? Well, I have the stoichiometry here, so I got to do that, right? So if already 2x NO2 I lose, I will gain x N2O4. And that makes sense, because they sort of just join together, right? So at equilibrium, my concentration of N2O4 will be x. And my concentration of NO2 will be 0.1 minus 2x. So hopefully we got at least that far. Now I'm going to write the equilibrium expression for Kc. So Kc is equal to NO2 squared. So NO2 is this one. Divided by whatever N2O4 is, and that would just be this. Now, if we talked about x is small, let's see here. Is this something that we can do just yet? Sorry, just a second. I want to make sure that... we have not gotten to that. Okay, so the intent of this problem is for us to just do the brute force the algebra here. Now, I could do all the algebra out for you again. We're not going to do that. We're going to go to Wolfram Alpha. Because that's what my intent for this problem should be. So let's capture Wolfram Alpha on the screen here. Boop, there it is. We need more on the screen than that. And I'm going to type my Kc expression, but I'm going to fill in all the variables. So Kc, according to our problem, was, what was it? 0.36. So let's type that in there. 0.36 equals, parentheses, 0.100 minus 2x, and I want that squared, divided by x. Solve for me. And so here's what it got once it allows me to scroll it. Oh, it shoved my solution all the way to the bottom. All right, so there's my solutions. And of those two solutions, one of those is invalid. So I certainly can't use this number, right? Oops, sorry, this one right here. This is way too big. If I subtracted 0.175 multiplied by 2 from 0.1, I would get a negative number, right? So, of our possible solutions, x must equal 0.0142225. 2225. 0.0142225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. 2225. So if X is this, then what that means is that the amount of N2O4 in the solution would be X at equilibrium. And the amount of NO2 would be 0.1 minus 2x. So we'll type that in here in the calculator. So 0.1 minus 2 times what we just got for x, which was 0.0142. And I get 0.0716. And there we go. That's our equilibrium concentrations. All right, and let's see if we're right by doing that. There you go. Oh, you know what? For my sig figs, hold on. So I don't actually get to keep these numbers. Actually, that one's okay. That one I can keep, but this one I don't. All right. Trying to get to the right screen here. There we go. Okay. All right, let's do another one. This one's going to be a KP, but it's the same process. So here you go. I want you to tell me the equilibrium partial pressures with these numbers. So I'll give you 5 minutes to get started. Then we'll go over the answers. So your partial pressure of I2 gas is 0.1 atmospheres. Partial pressure of chlorine gas is 0.1 atmospheres. And I've also thrown in some ICL. It is 0.1 atmospheres too. Oh, I had to sneeze there. I hope I muted myself in time. Go ahead and solve for these equilibrium pressures. Note that they are the same, so you might have an easier time solving, but you can always just use Wolfram Alpha for these practice problems. All right, we'll check in 5 minutes or so. All right, one more minute. We'll go over the answer. All right. So, I didn't set this one up, so we're going to just have to do that right here. All right, so I've got I2 and Cl2. 2 ICl. And I know that Kp for this expression will be whatever pressure of ICl I have squared divided by the pressure of I2 times the pressure of Cl2. That part we can do. Let's set up the ice table. And I put in 0.1 atm for all of these. These are reactants, so we're going to consume them. This is a product. We're going to generate it. And there we go. So we're going to plug all this into our Kp expression. So that's going to equal my products squared divided by my reactants. Now I got 2 of these. So I'm going to just write it like this. And then I'm going to square root everything so that this goes away. And that's I'm just writing that because it's simpler to type this in Wolfram Alpha. Because now I have square root of whatever Kp was, 81.9, equals 0.1 plus x divided by 0.1 minus x. And we can solve that. If we had to do this algebraically, this would be much simpler to do too. So we could just do it there. But we have Wolfram Alpha, we might as well use it, right? So, all right, so square root 81.9. That was the right constant, right? Let me just check. I can't tell because I have it hidden. Yeah, there we go. 81.9 equals 0.1 plus x divided by 0.1 minus x. Solve for me. What do we get? There is one solution, and it is 0.0800. So we have determined that x equals 0.0800. And since I am manipulating these to what looks like the thousandths place, I'm going to just get rid of this number because it's not going to help us. So that means that at equilibrium, the pressure of I2, I didn't mean to put a dot there, and the pressure of Cl2 are going to be equal to 0.1 plus that, which would be 0.180, and the pressure of ICl. Hey, guess what? We did all this wrong because I forgot a number. Let's fix this really quickly. Guess what I forgot? I forgot to do that. So that becomes that. That means that this number is different. I got to go back and fix this. Because I went to go multiply it by 2, and I was like, I didn't do that, did I? Okay, so let me make sure that captured the right number. So there, I updated the equation, and I got 0.0728 for that, which we're going to erase. I said erase. There we go. Well, I'll keep it in red because I had to update it. So I apologize for that. I'm going to make a bunch of math mistakes in this class because I'm bad at math. There we go. Oh, I got to put a 2 here too. There we go. And so PICL will be equal to 0.1 plus 2 times that number that we got. That's not times. 0.073. 0.246. There we go. And these aren't molarity, they are atmospheres. There you go. All right. So I made a minor mistake, which I corrected in red there. And this is why I want you to do your exams and quizzes in paper, because very easy mistake to make. Because look at all the chemistry we did. We set up all the equations correctly and did everything, but we forgot a 2 because of the stoichiometry. So how many points would that take off for you? I mean, if this was a 10-point question, I would deduct it by 2. Not because you forgot to write a 2, but because, 1, your answer is wrong at the end. And then 1 for, oops, I forgot this 2, which changed your answer. Everything else was correct, though. So I would give you 8 out of 10 if you made my mistake there. But Canvas wouldn't, which is why we're doing this. Oops, I got to scroll down to your answer so you can see it. This is why we're doing these on paper in person. All right. Hopefully, everybody was able to get towards that answer, which, interestingly enough, is not the answer that I... Oh, I see what I did. Oh, I can't even do basic algebra. Wow, I'm stupid. Okay. Guess what I did when I wrote these numbers down? Nobody's catching me, though, so I'm getting away with this. Yeah, what operation is this? This is a minus. What did I do? I added them. So I did 1 plus 0.73. I want 1 minus 0.73, which would be that. Because I went back to the other answers, which I can see, and I was like, wow, that's not what I got at all. I just can't do basic algebra. So now I have 7 out of 10 points. So good job. Good job, Professor West. You got a 70% on your own problem because you can't do basic math. That's okay. This is going to be a recurring theme for this class. It's not going to be the chemistry that gets you. It's going to be the algebra. So if my intent for that was to show you how easy it is to mess up a problem with just very basic mistakes, then hooray, I wish that was the intent. No, that was just carelessness on my part. All right. Now, we're actually going to introduce a technique in just a little bit that's going to make this a lot simpler. And so the odds of you running into algebra mistakes are going to be a lot lower. So I have one more problem for you to try, and then we're going to go on to the next topic. So go ahead and try this. It's the same problem, but I've just changed up the numbers. You should already have an ice table, so you could just copy it down again, rewrite all the numbers in there, plug it in Wolfram Alpha, and then tell me what your concentrations are. Or, I'm sorry, your partial pressures at equilibrium. Okay, so again, same problem, different numbers. So go ahead and give it a try. I'll give you 5 minutes. Type any answers you get in the chat so I know that you got them. All right, Maya says, 1 more minute, and we'll go over the answers. She just curled up at my feet. Hi, Maya. Maya, say hi. Meow. All right, let's go over the solution here. So this time I did set it up. Let me clear this out of the way so we have space. All right, so our initial concentration, so I2 is 0.150. Chlorine is 0.100. And ICl is nothing. We're going to consume reactants. We're going to produce products. I'm going to put the 2 in this time, so I don't embarrass myself. There we go. All my sums look correct. Okay, cool. So now that I've got my equilibrium concentrations, I'm going to plug those all into Kp. So Kp equals... So P squared for ICl, so that would be this squared divided by each of the pressures. All right. Now, because it's fewer characters, I'm going to scribble this out and I'm going to just distribute the squared. And then Kp is 81.9. So back to Wolfram Alpha we go. So we'll clear that. Oh, I should put it on the screen so you can see it. Boop, there you go. So that would be... All right, hopefully that looks good. And hopefully that's showing up on there. So I'm going to hit enter. And we're going to go boop. And we're going to see what happens. So what number did it spit out for me? I had 2 numbers. 0.09268 and 0.1701. Well, it certainly can't be the second one because that's too big. Because this is 0.15. I can't take 0.17 away from that. So x must be, for this expression, 0.0926. Which I'm going to write like this, since I can't really go past the third decimal point anyway due to the numbers that we have. So, at equilibrium, my pressure of I2 will be... Which one was I2? Is it the first one? Yeah, okay. So 0.15 minus that number. 0.150 minus 0.093. 0.057. My pressure of Cl2 will be 0.1 minus that number, which is most of it, right? 0.1 minus 0.093. I hit an extra button in there. And then P ICl will be 2 times the number we calculated, which would be 2 times 0.093. There you go. Now, if you're doing these problems and you're like, well, I just sort of got a bunch of numbers, How do I verify that these are correct? Well, what you can do is if you want to check, you can plug them back in to the equilibrium expression. You should get 81.9. So let's just do that real quick. So I should get, let's see here. Ooh, that's not what I want. I maximized the calculator and that freaked out my monitor. So we should, let's see here. So PICL squared, so 0.186 squared divided by, parentheses, 0.057 times 0.007, enter. And you'll notice that I got 86.7, which is close enough, and the reason that we have some error there is because I deleted a bunch of numbers, right? Like, I have a number with one significant figure there, CL2, because 0.1 minus 0.093 gives me 0.007. If I had more digits, I would get a closer answer. So I was off by like less than 10%, but that's kind of expected when you only have one sig fig. So our answer checks out. If we had these numbers to more sig figs, we could get a closer answer. But because we're in the ballpark, I'm going to call it good. All right. Let's make this simpler. Now that you've done it the hard way, let's make these problems easier, and you're going to see problems all throughout the quarter where you're allowed to do this. Okay? Now, there is a stipulation that you have to be careful of, and that stipulation is right here. KC or KP need to be small numbers. What that means is less than 1 for sure. But the smaller it is, the better the odds of this working are. Okay? This is called the X is small approach. And what X is small assumes is that, well, if I have a very small KP or KC for some reaction, so I'm going to just write a generic reaction on the screen here. So if K is small, then I would know that I have mostly reactants. And if it's small enough, eventually when I do my ice table and I get to my result, I'm going to have something like this, right? So I don't know, 0.1 minus X. If X is small enough, then the result of 0.1 minus X will equal 0.1, but only if X is small. And so what we can do is we could just say, okay, if it's that small, I'm just going to ignore it. I don't have to calculate it. And that's going to simplify our calculations to the point where we don't need to use Wolfram alpha anymore. Now, you can only apply X is small in these circumstances, but you only want to apply it to addition or subtraction quantities. So if your equilibrium expression looks like this, you are only going to X is small the bottom term here. So this goes away. Don't X is small the top, because otherwise you've erased all of your X's. You have nothing to solve for, right? So we're going to use this approach to simplify our problems. Let's look at an example here. So here's an example where X is small. If X is 5 times 10 to the 6, 0.2 plus that number is 0.2. Because it falls beyond the reach of our sig figs. We can't do that calculation meaningfully. So we can just ignore it. Now, what you have to do after you do this is you have to check to see that this is valid. Because if it's invalid, what ends up happening is the concentrations or pressures you get at the end of your calculation will have error in them. Now, they're always going to have error because we're doing an approximation. We're not using Wolfram alpha to solve for it for us. The rule is 5% error is allowed. And I'll show you what that means when we do a problem. Okay? So what you're going to do is you're going to check X versus whatever you're adding or subtracting it from. And if your number is 5% or more, of what you are trying to add or subtract from, x is not small. But if it's within 5%, so less than that, then you can do this calculation and you could trust the numbers that you're going to get. So let's do an example. So on the screen here, that's not the problem. On the screen here, I have this reaction, and we're going to assume that x is small. So let's go ahead and write out the expression for this. So first of all, Kc is equal to b squared over a. And that's going to equal 3.3 times 10 to the minus 5. So this is small, so we can use the x is small approach. So let's set up our ice table. And I have 1 molar A and nothing for B. We're going to consume A to produce B. Not 2B, but 2X. And then here's our expressions. 1.0 minus x, 2x. All right, so far so good? All right, let's put this all in the Kc expression. So b is 2x. That gets squared. And so there's a. I have a quadratic, but what we're going to do is we're going to say, okay, we're going to assume x is small. And so now my expression is Kc equals 2x quantity squared divided by 1, which reduces to this. Which then reduces to this. Which then reduces to this. And I didn't even need to go to Wolfram Alpha for that. So let's type that into the calculator here. So 3.3 times 10 to the minus 5 divided by 4. And then we're going to square root it. So way easier when you don't have a quadratic to deal with, right? But now we have to check that x is small. So let's do that. Let's find a place where we subtracted x or added x to something. And so that's this. So we're going to consider this. And so the way that you do this is you divide the smaller one divided by the bigger one. And then multiply that by 100%. And what you would get is you would get this. So my x was 0.287% of what I subtracted it to. That is less than 5%. So this is a valid approximation. So that means that for our pressures, or our concentrations, when we're done with this, and we go calculate the equilibrium expression, or with x in it, so A would be still 1.0, and B would be 2 times x, which would be 0.0056. To 2 sig figs. 5.7 actually, but that's close enough. Now to check our work, let's show that this was valid by typing all of this into Wolfram Alpha, which again I need to put on the screen. And so that would be Kc, which is 3.3 times 10 to the minus 5, equals 4x squared divided by 1 minus x. And we should get a number real close for x to what we got. And what did we get? Look at that. So we said x with our approximation was 0.00287, and they said 0.00286816. So our approximation saved us a lot of trouble. And this type of problem is now a problem that you can do on a piece of paper in a classroom. So this is what I'm going to basically be testing you on, is problems where the x is small approach is valid. Now, if I give you a problem and I say, use the x is small approach, and it turns out that when you do the check, it's like barely over or whatever, I will actually indicate that, because I do the check afterward too when I write these problems. So if I say, use the x is small approach if you want to, or if I just tell you to do it, please do so, even if you fall outside of the 5% range, because writing problems is hard. Like, I think I wrote on the quiz, for one of the problems, I said, use the x is small approach, even if it's invalid. And the reason for that is when I wrote the problem and I got the solution, I calculated it, and x was like 5.5%. And I was like, God damn it. I gotta write a whole new problem. And I was like, nope, you know what? It's fine. Just solve the problem. It'll be okay. So there's our ice table. There's our x is small going away. Boo! Oh, it's supposed to go away. There it is. And that's what we solve for. All right. When we come back, I'm going to give you this problem, which is a lot more complicated than we've done so far. Because I don't give you a molarity or a pressure. I just give you this. Whatever the hell this is. So we're going to come back to that after the break. So let's get more music going here. Hold on. I'm having technical difficulty with the website. All right. And then I will hit a button. Where is my button? I can't find the song I want. There it is. Alright, we are back. On the screen here, you're going to see a problem. And I have given you the information in a little bit of a different format. And my hint to you is, what is the definition of molarity? How would you find the molarity of something? Because remember, for Kc, we want concentrations. Kp, we want pressures. So if I give you it in some other format, you're going to have to rearrange your terms or your units so that you get what the units of K are asking for. Okay, so I'm going to let you try this problem. Do use the x is small approach because Kc is very small, so it's very likely that it will be a valid approximation. Once you've gotten your x value, check your approximation to see that it is valid. And we'll go over the answer in about 5 minutes. About 1 more minute, we'll go over the answer. All right. So what we're going to do here is we're going to go to this screen. Now, the first order of business is that I need numbers to put in my ice table. I gave you a number of moles and a volume, right? Well, molarity is moles of solute over liters of solution, right? So if my solute is H2S, that would mean I have 0.175 moles. I don't know why the M didn't appear there. Per, oops, not liter. Per 0.500 liters, or that. So this is what goes in the container to start. There's nothing else in here because I told you that I didn't say that there was. There you go. So then we're going to set up our ice table. So we're going to lose reactants. We're going to gain products. And so our expression would become, for equilibrium, 0.350 minus 2x, 2x, and x. So let's take all this and then we'll throw it in the Kc. So Kc is going to equal H2 squared, so that's going to be 2x, quantity squared, times S2, which is x, divided by H2S squared, and you could see what a nightmare this would be to solve by hand, right? Because we have a cubed term on the top and a squared term on the bottom. We're not going to deal with that. We're going to do this. We're going to say x is small. Where are we adding or subtracting x from? Right here. So we're just going to scribble that guy out. And now our term looks like this. So Kc equals, I'm going to distribute the squared, so I get 4x squared times x is cubed. Divided by that equals Kc. I'm going to just move this number over. Divide by 4. And cubed root it. And so we can type that all in the calculator now. We don't even need Wolfram Alpha. Or I could minimize the calculator and it could just go away. That also works. So Kc was 1.67 times 10 to the negative 7 times 0.350 squared divided by 4. And I'm going to raise all of that to the power of 1 over 3 for a cubed root. And that's what I get for x, 0.00172. All right, is it small? Let's check. Where did I subtract it from? I subtracted it from here. And you should be able to tell right away that this is going to be small. So times 100% divided by 0.35. 0.49%. So that means our approximation is valid. So if these are our concentrations up here at equilibrium, then H2S would be, we'll go down here, is 0.350 minus X, or minus 2X, sorry, 2 times 0.00172. And then H2 is 2 times X, so 2 times, oops, hold on. Not clicked on the calculator. 2 times 0.00172. Oh, my opacity is now 20%. Hold on, because I hit the 2 on the keyboard. Oh, undo. Why are you like this? Hold on. There we go. Can I undo this way? Oh my goodness, Photoshop, why are you so obnoxious? There we go. Okay, so there's H2, and then S2 is that. There you go. All right, we've done enough of these. The next two on here, so this one has an invalid X is small because of this reason right here. So Kc is small. Where'd my pen go? It's not even on the... There it is. Okay. Kc is small, which is okay. But if you have a very small initial concentration, then X is small is less likely to work. Less likely to work. And really all that means is that if you do this calculation and then you check X is small and you realize, uh-oh, it's too big, then you just go to Wolfram Alpha. And I literally have that linked in the slide. So I'm going to leave this one as an exercise for you to do because it requires you to do this on Wolfram Alpha. And then I have another practice problem here, same circumstance. You may or may not have to use Wolfram Alpha for this one, but I'm going to let you do that because we've done enough of these today. We've done like an hour and 10 minutes worth of them. So we're going to go on to the next topic, which is everyone's favorite, thermodynamics. Hey, remember this thing from 162? Remember delta G and delta H and delta S? Remember this expression? Oh no! What is this doing in Chem 163? So, what we're going to talk about in this section here is the conditions under which a reaction will proceed forward on its own. What does that mean? Well, delta G tells you if a reaction happens, right? If delta G is negative, then the reaction is spontaneous. It'll just go on its own. You don't need to provide any input. And also, if delta G is positive, the reverse reaction is spontaneous. Now, why is that relevant to us? Well, we're talking about equilibrium, right? So delta G must be related to which direction a reaction will go, primarily. And it is. And we're going to relate delta G to the equilibrium constant to round out chapter 13, which will be the last thing that we do. Unfortunately, probably not today, because we're going to need more time. So there's our summary right there. I didn't include process that is delta G equals 0 is at equilibrium, but that makes sense because if we put a 0 in for that, we would get delta H equals T delta S, and we can use that to solve for a specific temperature at which equilibrium would occur for a given delta H and a delta S. Let's just show that right here. So if delta G equals 0, then I get this. Delta H equals T delta S. And for a given delta H and delta S, we can find out which temperature will generate a reaction that is just at equilibrium. So that's going to be cool for us because we could say, okay, I have this reaction and I know these thermodynamic constants. Delta H and delta S are just in a table in the back of your textbook. And they're known for virtually every substance because we've been doing thermodynamics on these substances in laboratories for forever, basically. So if I have any reaction and I want to figure out what temperature I need to heat it to get it to equilibrium, and then I can heat it past that or cool it below that to make the reaction spontaneous, we can figure out how to make any reaction go in our favor. Potentially. Some reactions is going to turn out will never be spontaneous. So what we're going to do is we're going to look at delta H and delta S, and we're going to look at their signs, because the signs will affect the results of our expression. If I have a delta H and a delta S, and one of them's negative, I'm going to get a temperature that is negative. And remember that this is going to be in Kelvin. If you get a temperature that's negative for Kelvin, that's going to mean something interesting, right? So the signs are going to matter for our discussion here. So we need to consider them. So let's look at this first situation. Let's suppose that I have a negative delta H and a positive delta S. Remember that an exothermic reaction releases energy, and something that produces entropy, so like entropy is increasing in the universe, is also thermodynamically favorable, right? So this term, delta H, will be negative. Delta S is positive, but there's a minus sign right here. So this overall term will be a negative minus a positive, which equals something that is more negative, right? So overall, delta G will be negative under these conditions, regardless of what numbers you enter. You can put any negative number for delta H and any positive number for delta S, and those terms will just complement each other. They will become more and more negative. So this reaction, when I punch all of this information in, regardless of what temperature I get, I am going to get a negative delta G. So this reaction would be spontaneous at any temperature you want. So if delta H is negative and delta S is positive, spontaneous at all temperatures. Cool, let's do another one. I'm going to flip the signs here. So now I have a positive number. I'm going to subtract that from a negative number, which is basically or I'm going to subtract positive minus a negative number, which is like adding, right? The end result is that no matter what numbers I have in there for delta H and delta S, if they're both these signs, delta H is positive, delta S is negative, I will always get a positive number for delta G. And what that means is this reaction will never be spontaneous at any temperature. The reverse reaction would be spontaneous. For the next few, we're going to have a situation where these terms don't complement each other anymore. So if I have both the same sign, here's what happens. If I have a negative value for delta H and a negative value for delta S, this term right here is positive. Which means that delta G will be negative. Let me write it over here. So delta G is negative if T is small. Because for a small temperature, I will have a small positive number, and it will be smaller than my negative delta H. But if temperature is very large, then that positive term will eventually dominate our delta H negative term. And as a result, delta G will end up being positive. So if T is large, then delta G is no longer spontaneous. So a reaction with these terms, where both are negative, delta H and delta S, will be spontaneous below a certain temperature. What that temperature is, we're going to have to set delta G equal to 0 and solve for T and see what we get. So this would be an example of an exothermic reaction. Which makes sense, right? Because if we have something like this, delta H is negative, so that means it's exothermic. Heat comes out. If I make T large, the reaction is going to have too much heat, and we're going to drive the reaction back towards reactants, right? That would be the opposite of a spontaneous process. So the reaction is spontaneous at a low temperature. So this satisfies Le Chatelier's principle. That's cool. That's a thing we learned about on Wednesday last week. So we've come full circle, kind of. It's a tiny circle. We're going to make bigger circles as we go on. Finally, the last circumstance here. If delta H is positive, which means it's endothermic, but entropy is also positive, this term right here is negative. And thus, delta G at low temp is positive, but delta G at high temp is negative. Sorry, there's a car backing up outside my window. Hopefully you can't hear it. It's super annoying. So for this reaction with these signs for my delta H and delta S, my reaction will be spontaneous above a certain temperature. And I can do the same thing as before. Because it's endothermic, delta H is positive. If I increase the temperature, the reaction drives forward and is more spontaneous. So that's neat that these reactions match up with our understanding of Le Chatelier. So let's do an example of this to figure out whether a reaction will be always spontaneous, non-spontaneous, or spontaneous above or below a certain temperature. Anyway, here's the summary chart for you of everything that we just talked about. So you can refer to this chart if you need it for your practice problems. Obviously, on a quiz, well, quizzes are take-home anyway, so you could use this as your reference. But on an exam, you would want to have this memorized. All right, let's do an example. I want to turn carbon tetrachloride into graphite and chlorine gas because I guess I just need pencil lead. I don't know. If you need to turn your carbon tetrachloride into graphite, you're pretty desperate. There's some thermodynamic terms that I looked up and calculated from the back of the textbook. At 25 degrees Celsius, will this process be spontaneous? Let's find out. I'm just setting this up here real quick, so... There we go. Okay. So delta H is positive. kilojoules per mole. Oops, we don't need to write per mole. And delta S is positive 142.2 joules per Kelvin. And there's our equation. Will the process be spontaneous at 273, sorry. So temperature equals 25 degrees Celsius, which is 298 Kelvin. So we're going to plug this all in to this expression. So delta G would equal 95.7 kilojoules. What I'm going to do is I'm going to do this. Why did I do that? Because I don't want kilojoules and joules together. They don't sum, right? So I'm going to make everything joules so that when I do the expression here, my units will cancel out. So my kelvins cancel out here. And so I have 95,700 joules minus 298 times 144.2 joules. So the end result I'm going to get is in joules. Let's see what my calculation is. So 95700 minus 298 times 142.2. And so I get this. I'm assuming this is the last sig fig, so this is going to be my result. Or positive 53.3 kilojoules. So is this reaction spontaneous? So I got a positive number, so not spontaneous at 25 degrees C. In other words, the equilibrium constant at this temperature would be less than 1. All right. What temperature will this process be spontaneous, if ever? Well, let's find out. So if I take this expression and I set this equal to 0, then my expression becomes delta H equals T delta S. I moved this term right here over to the other side, and then I'm going to divide by delta S to get just T. And so I know my reaction is endothermic, so it's going to be spontaneous above T. Why is it endothermic? Because delta H is a positive number, right? So we got that up here. Okay, so let's do the calculation here. So I've got 95,700 joules divided by 142.2 joules per Kelvin, which is going to give me an answer in Kelvin. Oops, I shrunk the calculator. I didn't mean to do that. 95700 divided by 142.2. 673 Kelvin. And so we would conclude that it is spontaneous above 673 Kelvin. And we know that it's above because the reaction is endothermic. So we need to heat it above 673 degrees Kelvin for this to happen. So this is a super powerful tool that we have. You could take any reaction that you have delta H and delta S for, which, using the numbers from the back of your textbook, is every reaction you can think of, and determine whether the reaction is spontaneous or not at a given temperature. People would pay a lot of money for that information, and I'm giving it to you for free. That's why I'm a terrible businessman. All right. I want you to try and do this problem here. We're going to hydrogenate ethylene. So ethylene is a compound with a double bond, and sometimes you don't want double bonds. You want to get rid of them. Here's some thermodynamic data. I'm going to write down the equation. I'm sure that you have not memorized this yet, unless it is something that you did last quarter. There's the expression again. I want you to tell me if this reaction is spontaneous, and does delta G become more negative or more positive as I increase the temperature, and what temperature, if any, at any temperature, this becomes spontaneous. So we'll add that one down here. What temp is it spontaneous? Because I just noticed that this problem is incomplete. You can't solve that first problem. You need a temperature. So there you go. So tell me, first of all, with those numbers, is the reaction spontaneous at 25 Celsius? And then what temperature range is it spontaneous? And tell me if delta G increases or decreases as temperature increases. I'll give you 5 or 6 minutes to play around with that. We'll go over the answers, and then I don't think we have that much time left, so we'll see what we can do after. All right, we're going to run out of time unless I go over the answer here. So let's do that. So clear the canvas there, and we'll put this on the screen. Oops, there we go. All right, so let's check if it's spontaneous. So delta G equals delta H minus T delta S. And so at 25 degrees Celsius, which is 298 K, I would have minus 137, 500 joules, minus 298 Kelvin times negative 120.5 joules per Kelvin. And so we get, so negative that, minus, parentheses, 298 times 120.5, negative. And it's a little less negative than delta H is, but it's still negative. All right. Now, because delta S is negative, it's not is delta S negative. If delta S is negative, increasing temp means delta G becomes more positive. Now, why is that? Because this negative and this negative cancel out, become a positive. Boop, boop. And so now as this number grows, I am adding a larger and larger and larger positive number to this. And eventually I will hit 0, right? And then at that point, the reaction is no longer spontaneous. So let's find the temperature at which this is no longer spontaneous. So that's going to be where delta G equals 0, because the reaction will be at equilibrium. And because this reaction is exothermic, I want a temperature threshold below the T that I'm going to solve for. So that's going to be minus 137,500 divided by negative 120.5. These both become positive. And what do I get? I got 1,141 Kelvin, which is what you got. Very good. So any temperature below 1,141 Kelvin, the production of ethylene into ethane by adding hydrogen to it will be spontaneous. If you go above that temperature, the reverse reaction is spontaneous, and instead it falls apart. Now, you're going to notice a trend with that. If you have a reaction where you're decomposing something, it's spontaneous at high temperatures. And if you have a reaction where you're combining things, they tend to be spontaneous at low temperatures. And the reason for that is at the highest temperatures, everything just sort of falls apart, right? Things just break. So if you have a reaction that's decomposing, which would be the reverse of the reaction you see here, higher the temperature, the easier it is to do that. All right. Now, Unfortunately, I don't think that we have enough information covered to finish the quiz, because I just looked at it, and there's one question at the very end that you can't solve just yet, because we haven't gotten to this expression, which is way down here. Where's my RTL and K? I'm trying to find it. I don't see it because it's so tiny. It's somewhere in here. It's one of these. But there's an expression that is just delta G equals RT ln K. And it's somewhere in here. Whatever. I don't give a shit at this point. We're not going to finish it. So I'm going to postpone your quiz. Your quiz will be due next week instead. I'm going to send out an announcement about that after class. So what that means is that on Friday, you don't want to bring in quiz number 1 or quiz 13. It won't be due. But if you have questions about it, you can ask me, and I can't tell you the answers, but I can point at, like, I can hint strongly, like, do this problem again, or you didn't show your units, or this delta H is not in joules, or stuff like that. I can give you suggestions, because I want you to get a good score, obviously. So if you have questions about quiz problems or homework problems or anything, and you're doing the lab and you're just waiting on a titration or something, we can use that time wisely. I have a whiteboard. I have all the pens ever. I know all these problems like the back of my hand, so I could do all of them. And if that helps you, like, please, by all means, use the lab time wisely. I do want it to be more than just lab because, I mean, I've never taught a hybrid class before, so this is kind of strange to me that this is the only time I will see you in person is Friday from 9 to 12, and I'll stay later if I need to. Just I need to go to Taco Book at some point to get fit. And you can follow me to Taco Book. Taco Book's really good. And then we can talk about stuff while I eat. Or maybe even while you eat if you want to buy food too. So that's going to be my plan for Friday is you're going to do an experiment. I'm also going to give you a lab primer, which is just a little 20-minute exercise of find all the shit in the lab and then show me you know how to use a burette and a pipette. That shouldn't take any time at all. Yeah, that's what I see. That's how I see Friday going. Please, please, please don't be late. If you are late, that's going to make it really obnoxious for other people, particularly if you have a lab partner or if you don't have a lab partner. So, yeah. Yeah, that's all I got. I don't have my music up, though, so hold on. Gotta find that. Still looking. There we go. Okay. Ta-da, there we go. Alright, so we'll keep working on Chapter 13 next week on Monday. We'll finish it then. See you on lab on Friday. Take care.